Hello, stat students. Today we are learning about confidence intervals. This is going to be what makes up the second half of our unit, and it's a really important concept. So basically, how confidence intervals work is we get a sample, and of that sample, we get a sample proportion, P. And we use P as an estimator of the population proportion, pi. Well, given a distribution, if we don't know pi, we can use p. And we can say, okay, this distribution is centered at p. However, we're never going to assume that a sample statistic is going to be exactly the same as a population parameter because we know that there is a lot of variation in sample per sample. So we're going to say, okay, we're going to use p to approximate the distribution, but we have a certain degree of confidence that the true population proportion is somewhere within these bounds. So we kind of estimate what we think the center is, and then we give ourselves a little wiggle room just in case. So what is a confidence interval? Okay, a confidence interval, more formally, is an interval of plausible values for the particular population characteristic. We construct this interval so that with a chosen degree of confidence, the value of the characteristic will fall between the upper and lower boundaries of the interval that we create. And so what is a confidence level? This is the success rate of the method used to construct the interval. Okay, so this is going to become a little bit more clear. Here's how we create a general confidence interval formula. So how do we get these two bounds that we mentioned above that are giving us a little padding around what we estimate the true population proportion to be? Well, here's what it is you take your estimate, and this is true for numeric, non-numeric data, whatever, and then we'll make it more specific below. Estimate plus or minus something we use called the critical value times the standard deviation. Okay. All right. So there's our general formula. Okay, so now we're going to talk about how to make a confidence interval for proportions. So when we say proportions, we mean numeric data. So here's our formula for numeric data. It's our estimate, which would be P. I'm using P in pi notation. Plus or minus a critical value. Okay, a critical value for a P distribution is a z-score along the standard normal curve that we will talk about that draws a boundary for our degree of confidence, okay? So we're going to get to that at the end. We call that critical value a z-star times our standard deviation, which is the square root of P1 minus P over N. Now there's something that needs to be said here because normally we use pi for this formula. However, pi is what we're estimating, okay? So we must use P for calculating the standard deviation because we do not know pi. Pi is actually what we're building the interval to approximate, okay? So there's no way we can know it. So if we're trying to find the true population proportion, there's no way we're going to have it. So this formula follows exactly the more general form above. Our estimate is P plus or minus, because we're going to go on either side of our estimate, a critical value times the standard deviation, okay? And this equals our plausible values. This gives us our interval of plausible values for pi. Okay, so here's what it kind of looks like. Just again, to reiterate, is we have a distribution, we get a p-value, and we say, okay, I think that pi may fall right here also. And then we go, well, you know what? Just to be sure, I'm going to build out from this predicted value a little bit. I'm going to give myself some margin of error. That's what this is called on each side, margin of error on each side. And I'm going to say that it may not be true that pi falls exactly in the same spot where p is, but I'm pretty sure, and I will have a certain confidence level, a degree of confidence that we'll discuss in a minute. I'm pretty sure that it falls somewhere between these two bounds, okay? It's important to note that your margin of error is the amount of wiggle room you have on either side of your estimator, okay? And one important thing that you absolutely must know is that your margin of error is half the width of the confidence interval. Is half the width of the confidence interval. Okay, and before you can do any of this, you do need to check your conditions. And these conditions are exactly the same four conditions that you guys use on your quiz. And that's 1, that it's random, 2, n times pi, or in this case you have to use p because we don't know pi, is greater than or equal to 10. N times 1 minus p is greater than or equal to 10. And n is less than 10% of the population. Okay, so you need to check these conditions before you build an interval as well. Let's talk about this thing right here, this critical value, okay? So critical value is a z-score. It's a boundary. So basically what your critical value is it's the z-score for either the upper or the lower. It doesn't really matter because we add and subtract this product anyways. It's the boundary line, the z-score for either your upper or lower boundary after the margin of error, okay? So let's see. Our most common critical values we're going to write down after we learn how to find just one critical value, okay? So how do we find critical values? We use inverse norm. Okay? So let's write this out. A critical value is a boundary on the standard normal curve. Okay? Something that goes hand in hand, and I know this is a lot of vocab being thrown at you, and we're going to spend quite a bit of time reviewing this with both proportions and numeric data. But another thing that goes hand in hand with this is something we call our alpha level. Our alpha level, represented by the little fish symbol alpha, is the amount of error we will allow outside of the confidence interval. This is inversely related to the confidence level. So if our confidence level is 90%, our alpha level will be 10%. Okay, they're inversely related. So they add to 1 together. Alpha is split into 2. So we're allowing whatever our alpha level is divided by 2, that amount of error in each tail. Of the distribution. Okay, so let's find some critical values together. Okay, our most commonly used confidence interval sizes are 90%, 95%, and 99%. So this is when we say, I'm 90% confident, I'm 95% confident, I'm 99% confident. Can you be at any degree of confidence? Yes, but those are the 3 most common ones. So after we calculate those critical values once, you can use them over and over and over again anytime you see them inside of a question. You can just memorize the corresponding critical value. Okay, so let's check this out. Let's find the critical value, or that Z star value. And so we'll just remind ourselves this is also called Z star. For a distribution that we're looking at when alpha equals 0.10, which means that for that distribution we have 90% confidence. What does this look like? Okay, here's what it looks like. We've got a distribution. In order to find this Z-score, we're using a standard normal curve centered at 0 with a standard deviation of 1. And we're looking for some kind of boundary lines here. We're looking for the boundary lines. And below the mean, I'm going to have a negative Z star value, a negative critical value, and above I'll have a positive critical value. You can use, either one, negative or positive, because in the formula we add and subtract anyways. Okay, so if I want 90% confidence on my standard curve, I would have my predicted population proportion here and my standard deviation, and I would say I'm predicting that I'm 90% confident the true population proportion lies between these 2 values. So I have 90% confidence that it's gonna fall inside this interval. And then I have 5% or 10% of doubt. Okay, I have 10% of error. So I'm allowing 5% of error on this side and 5% of error on this side. And if you notice, this adds up to 10%, which is 0.10. That's our alpha level, okay? So alpha is the amount of error we allow in the tails. It's divided by 2. So if I have 0.10, I have 0.05 in each tail and 90% confidence in the middle. So how do I find these critical values right here? How do I find this Z star value? Well, I use inverse norm. 0.05, because that's my area to my left. Remember, I always read to the left, 0 and 1. And we get a Z star value of negative 1.645. And what if I wanted to use the positive Z star value? Okay, it's area to the left, which is 0.95, 0 and 1. And I would get positive Z star value of 1.645. So our critical value for 90% confidence is always going to be 1.645. Okay, so you can do this process every single time. You can find out that critical value by using inverse norm, or you can just memorize them. Either way. Okay, let's do one more. Let's find our critical value when alpha equals 0.01, which means we have 99% confidence. Okay, what does this look like? This means we have a curve centered at 0 and 1, and I have a certain boundary that I'm allowing out, certain margin of error, and I have 0.01 to share between the tails. I've got 0.005 and 0.005 on each end, and I've got 99% in the middle. Okay, so I've got a negative z-star value here representing this vertical line, and a positive z-star value here representing that vertical line. How do I find them? Inverse norm. Area to the left is 0.00501, and I get out approximately 2.58 negative. And inverse norm, area to the left is 0.99501, and I get a positive 2.58. They're always going to be exactly the same, one negative, one positive. Okay, so we can find any z values for any level of confidence, but these are our particularly common levels of confidence. Okay, and so 95%, I'm going to just give it to you. We don't have to calculate it right now. This is 1.95. Okay, here's some things that you need to know about confidence intervals. Okay, the more confident you are, the wider the interval. So this can be tricky because you want to be careful that you don't make your interval too wide. For instance, I could say, I'm 99% confident all students at Claremont High School are between the ages of 2 and 75. Okay, of course. That's such a wide interval, everything falls in between. It doesn't tell me much. So later on, we're going to look at how we make sure those things don't happen. But it is important to understand that the wider the interval, the more confident we are, because we're just opening it way up. Okay. Also, when you have a confidence interval, there is a particular way we need to interpret it. So here is how you are going to interpret your confidence interval. This is one of those things you kind of need not to memorize, but you need to know. Okay, so we are blank percent confident that the population proportion and of course this needs context. I forgot the word true. That the true population proportion falls within the interval of blank. Okay? Really, really important. Okay, I'm going to pause the video now and I'm going to write an example below. And you guys should pause and write it down and do this one with me. Okay, so here's our first example. A doctor is testing a new medicine. He claims the medicine, oops, I accidentally wrote this twice. I got distracted. You guys are taking your quiz right now and someone's talking to me. Okay, we're back. He claims the medicine cures well over 45% of the patients. He runs a test on 100 patients and 51 are cured. Does this sample support his claim with 95% confidence? Okay, so let's check this out. He's claiming he cures well over 45%. Let's see. So we've got some work to do on the side first. P, or our sample proportion, is 51 out of 100, which is 0.51. And on this section, we're only doing categorical questions. But if you weren't on this section, it was just anything else, you would want to say, is this numeric or categorical? And we know this is categorical because you're either cured or you're not. There's no measure, okay? Okay, now we have some conditions to check. So let's check our conditions. Number one, it's a sample random. We're going to assume. Okay. Number two, 0.51 times 100, that's 51, that's greater than or equal to 10. And then 0.49 times 100, is that greater than or equal to 10? 49, yes. Step 4 is our assumption that 100 is less than 10% of the population. All right, here's what I do for all of these problems. Is what we are calculating here is called a one proportion z interval. And I always write down the formula exactly the way it is right after. It's p plus or minus a z star square root p1 minus p over n. All right, and then I just fill everything in as I go. So let's do this. P is 0.51 plus or minus a z star value. I want 95% confidence, so I can either calculate it using inverse norm, or I can just go look at my table above. For 95% confidence, we have a critical value of 1.95. Okay, so we can just use that one every time. Okay, so times 1.95 times the square root of 0.51 times 0.49 over 100. And I'm going to use my calculator just to crunch all of this down. And after you do that, you should get 0.412 to 0.608. Just try and make sure you do that yourself, okay? So what does this mean? This is the important part. It means we are 95% confident the true proportion of patients cured is between 41.2% and 60.8%. Okay? And so the question asks us right here, does the sample support his claim with 95% confidence? And remember, his claim was that the medicine cures well over 45% of the patients. Well, we're saying that we're confident that it can cure, it really cures anywhere between 41 and 60%. So are we positive it's above 45%? No, because there's a chance that it can fall below 45% all the way to 41 possibly. So what we did here is we have a distribution with a sample, and that sample gave us a value of 0.51, and we said, okay, that's the true proportion for this sample. We think that the true proportion for everybody is gonna fall somewhere between 0.412 and 0.608. So we're not gonna commit and say it's exactly 0.51. We're gonna give ourselves a little bit of space with 95% confidence, so there's a 5% chance that we could be wrong and the true population proportion could be out in the tails. But we're 95% confident it falls between these two bounds, okay? So the answer to question is no. since the boundary falls below 45%, there is a chance pi is less. Okay, so for today, you do have 4 practice problems that are due by Thursday. So you have today and tomorrow to get these done and get those practice problems in. Your formula is really important, and make sure you follow your steps to finding a critical value. We will go over all questions on Thursday. Make sure if you missed anything, you pause, you watch, you rewatch, listen, get questions prepared for this video because it's a very important lesson. All right, I'll see you guys on Friday. Bye.